Good morning, Team Alabama. We are going to continue reading in Hidden Figures. Please find it on page 51. You're going to add to your facts today, your questions, and your vocab. Page 51, what makes things fly? The pace of discovery and invention was so fast at Langley that an entry-level position there was considered by many people to be like studying at the world's best engineering school. In addition to receiving on-the-job training, employees had a chance to take classes in math and physics and other subjects that would help them further understand how to design better planes. Those would be great facts to add. That entry-level jobs were really respected and like being in a school. And also then they had chances to take additional classes outside of their work. And that's what Dorothy did. With the goal of turning women math teachers into crack junior engineers, the laboratory sponsored a crash course in engineering physics for newly arrived computers. 2 days a week after work, Dorothy Vaughan and other new mathematicians filed into a makeshift classroom at the laboratory for an intensive class in the fundamental theory of aerodynamics, which is the study of objects moving through the air. So there you go. There's a great vocab word for you right there, aerodynamics. And then the definition would be the study of objects moving through the air. They also attended a weekly 2-hour laboratory session for hands-on training in one of the wind tunnels. Okay, there's another great fact. And they had an average of 4 hours of homework on top of their 6-day work week. So they worked 6 days a week and they had an average of 4 hours of homework. What makes things fly? Dorothy asked herself all day long at her new job. She had never flown on a plane and had never before given much thought to the question. The first course she took at Langley taught her the basics of aerodynamics. She learned that when a wing moves through the air gets cut into two parts. There is a slower moving air on the bottom. So the slower moving air is down here. Okay. And the faster moving airflow on the top. So the faster moving air is up here, the slower is on the bottom. Okay. And this creates two different pressures. And it's this pressure, or this difference in pressure, that creates the lift. The almost magical force that causes the wing and the plane attached to it to rise in the sky. It's important to keep air smoothly flowing around the plane. Turbulence, or sudden gusts of wind, there you go, there's a great vocab word, turbulence, a sudden gust of wind, can make a plane hard to control. One of NACA's greatest achievements was designing wings that allowed planes to move easily through the air. Today, we take many of these design elements for granted. But each change came about after a series of experiments and mathematical computations and luck. The first inventors made some assumptions. They built a plane and they tried to fly it. And if they didn't die in the process, they applied what they learned to the next attempt. By the time Dorothy was on the job, the task of modifying airplane design had been turned over to the aeronautical engineers and the test pilots who flew the planes directly into their weak spots. Each time the pilots pushed the aircraft to the limit, they helped generate data that could be used to identify ways to make a good plane even better. The test pilots also risked their lives and the loss of a very expensive piece of equipment. To make the job easier, researchers developed wind tunnels that allowed them to test model planes without the danger of flying a real plane. At its simplest, a wind tunnel was a big box attached to a powerful fan. The basic idea behind the wind tunnel was that air moving at a certain speed over a stationary object was similar to moving the object through the air at the same speed. Engineers blasted air over full-sized aircraft, scale models, or individual parts, such as wings or bodies. By closely observing how the air flowed around the object, the engineers could assess how the object would fly through the air, and Langley built different wind tunnels to test specific features of the planes. There was even a tunnel called the full-scale tunnel, which opened wide enough to swallow a full-size plane. Running the electricity-hungry wind tunnels wasn't always easy for the laboratory because the local power company rationed electricity during the war, including for the laboratory. The NACA solved the problem by running some of their tests into the wee hours, and people living near Langley complained about the roar of the tunnels while they were trying to sleep. Despite the challenges, building wind tunnels that were quite similar to real-world conditions was one of the keys to NACA's success. So wind tunnels helped them succeed in building these planes and figuring out where the trouble was. Making a good plane better. No organization came close to Langley in the quality and range of wind tunnel research data. It wasn't good enough to say a plane flew well or badly. Engineers tried to measure how a plane performed, so they developed a 9-page checklist. Okay, there's a great fact for you. When they were working on improving a plane, they had a 9-page checklist. These experiments generated data, numbers, and lots of numbers, and the raw data from the tests then went to the desks of Dorothy Vaughan and the other female computers for analysis. An airplane wasn't one machine for a single purpose. It was a complex machine that could be tweaked to perform different kinds of tasks. The airplane's names or designations reflected their use. Fighters, also called pursuit planes, were assigned the letter F or the letter P for fighter or pursuit. The letter C identified cargo planes, which were built to transport military goods and troops. B was for bombers. X marked the spot of experimental planes still in development. Planes lost their X designation once they went into production. So while they're building them and working on them and testing them, they're an X. For example, the B-29 was the final version of the XB-29. Engineers worked hard to make each version of an aircraft better and more stable than the previous one. Discoveries, large and small, contributed to the speed, maneuverability, and the safety of the machines. Okay, maneuverability would also be a great word to add. It means that it moves easily, or how something moves. As World War II approached its peak in 1945, almost every American military airplane being produced in factories had features that were based on the research results and recommendations of the NACA. Okay, here's a picture of the B-29 Super Fortress. Okay, it's on your page 55. Whether data came from the wind tunnels, test flights, or theoretical models, it eventually reached the women computers so they could use their sharp pencils and sharp minds to figure out what the numbers meant. Instead of looking at just a few numbers, they looked at extremely large sets of numbers, which could be used to find patterns or trends in the ways the airplanes performed. What Dorothy and the other women at the laboratory worked on was usually a small portion of a larger task. The work was carved up into smaller pieces for quick, efficient, and accurate processing. By the time the work arrived on the computer's desk, it might be just a set of equations and numbers. Sometimes, they didn't even know what kind of plane had been tested or what the engineers were hoping to understand from their research. Once a woman finished a particular job, the calculations were taken to the engineers who used them to improve airplane design. The computer's work was essentially but largely uncelebrated. Woe unto thee if they shall make thee a computer, joked a column in Air Scoop. For the project engineer will take the credit for whatsoever thou doth that is clever and full of glory. But if he slippeth up and maketh a wrong calculation, he shall lay the mistake at thy door, when he is called to account, and he shall say, what can you expect from a girl computer anyway? So the men engineers take all the glory, and if there's a mistake, they blame it on the computers. But sometimes a breakthrough was so important that everyone got credit. When the Boeing B-29 Superfortress was finished, it became a symbol of the United States' technological progress and its ability to bring destruction to its enemy. There is no one in the laboratory who should feel that he or she did not have a part in the bombing of Japan, the NACA director said to the lab employees. The engineers who assisted, the mechanics, the model makers who did their share, the computers who worked up the data, the secretaries who typed and retyped the results, and the janitors and maids who kept the tunnel clean and suitable for work, all made their contribution to the final bombing of Japan. Dorothy knew that her work was making a difference in the outcome of the war. She read the news accounts of how the B-29s, capable of flying farther, faster, and with a heavier bomb load than any plane in history, dropped precision bombs over Japan from high in the sky. Dorothy found her work more intense and interesting than she had imagined, and she knew that she wanted to stay for the duration of the war, and maybe longer. There was no doubt about it that Dorothy Vaughan had become one of the NACA nuts. We're going to stop there for today. That's the end of Chapter 7. Have a great rest of your day, Team Alabama. Please add several facts and several vocab today.